Hey everyone, my name is Mark Cunningham and I'm really excited to talk today at the Northern Ireland Developer Conference. Today I'm going to be talking about quantum computing, what is it, how can we get involved in it, and I'm going to talk more in depth about a package called Qiskit, which allows us to use quantum computing. Um, so a bit about myself. I'm an undergrad physics student at Queen's University Belfast. I have a very keen interest in quantum mechanics and electromagnetism and optics. I recently just dropped out of the astrophysics pathway as I feel that I want to devote my career entirely to quantum mechanics. I'm a collaborator at Artificial Intelligence Northern Ireland, or AI&I for short. Obviously, it's been a bit quiet lately. And more related to this topic today, I'm a Qiskit advocate at IBM Quantum. So basically, my job there is to tell everyone about Qiskit and get involved in the community. So, content summary of what we're going to be talking about today. What is classical computing? What is quantum computing? And then what is Qiskit? And then I'm going to show you a bit about how to get involved and what Qiskit looks like. So, what is classical computing? It's what we use day to day. It's a normal computer that all of us are familiar with. We store information in bits, 0 or 1. A bit is the smallest unit of information. 1 is on, 0 is off, sort of like electrical pulses on a circuit board, and it can only be one or the other. We use logic gates to perform operations on a computer, and or XOR, NOT, etc. on a collection of bits, which allows us to process information in the way that we can today. We perform these logical operations using transistors, which are tiny pieces of hardware on our circuit board. So what's quantum computing? The main difference between classical computing and quantum computing is that we use quantum bits to store information, or qubits for short. So like a bit can have a value of 0 or 1, a qubit can have the value of 0, 1, or a superposition between the two. So it can have many possible states at the one time. When measured, a qubit collapses to either 0 or 1 with a probability depending on its latitude on the block sphere, which we can see here. But it can hold so much more information than one bit in a superposition. So as we can see in this image here, we have a classical bit, 0, 1, and a qubit can be anywhere around this sphere here. You can't really see there, but this is down here, the state 1. So, a deeper look at superposition. What is it? Why is it useful? In quantum mechanics, we can only calculate the probability of the value of a physical quantity being measured. So in this graph here to the right, we have one qubit in a superposition between the state 0 and the state 1. And you have a 50% chance of that whenever you measure this qubit, it will be either 0 or 1. When you measure it, you won't be able to see that it is in a superposition. It collapses to one of those values. So how does superposition actually help? Why is this useful? Why do we even care about it at all? A good analogy is this maze here with 4 possible paths to an exit. A regular computer tries every path one at a time, so 0, 0, 0, 1, 1, 0, 1, 1, going through this array, whereas a quantum computer can represent all of these combinations at the same time in a superposition. So let's say this was an array that was thousands and thousands and thousands of units. A quantum computer can represent all of those states at the same time. So with every additional qubit, the number of states you can represent doubles. So for 64 qubits, you have this huge number here of possibilities, or maze paths, if we're continuing the analogy, all at once, which is roughly 1 million terabytes. A computer with 64 bits can calculate this too, but only one at a time. It's going to take absolutely forever. Roughly 400 years of processing, with each state calculated at about 2 million cycles per second. So, how do we make a qubit? How does it physically work? So there's a few different options, but the main 3 are atomic nucleus, which is basically the direction of the magnetic moment can point in different directions with respect to magnetic field. But the challenge there is in placing and addressing that single atom. There's also a trapped ion quantum computer, which is basically you strip an electron off of an atom and turn it into an ion, and then you use electromagnetic fields to suspend the ion in free space and firing lasers at it to change its state. And then you can have a photonic quantum computer, which I find the most interesting, which is where a packet of light can be in superposition in the direction that it's waving, and you can assemble quantum circuits by sending photons around a maze of optical fibers and mirrors. So this is where I introduced Qiskit. So Qiskit is the quantum computing package made by IBM, and it is a Python open source package, and it stands for the Quantum Information Science Kit. So it provides tools for creating and manipulating quantum programs and running them on actual real quantum devices on the IBM Q Experience or on simulators on your local machine. So it uses Python. I've been programming in Python since I was 13, 14. So that it made the field of quantum computing really accessible and easy for me to get stuck into, whereas normally it could be quite difficult. And what's really important to mention is that the future of quantum computing is cloud-based. I find it absolutely crazy that you are able to use an actual quantum computer from your laptop in your living room, or in my case, my bedroom, rather than actually having to be in a lab. I think that's absolutely amazing. So this is the IBM Q Experience. This is an old screenshot, but basically it shows you what recent circuits you've run, pending results that you're waiting for. To the right here, you can see that there's different quantum computers, each that have a different number of qubits with a Q on them, and then you're able to actually run Jupyter notebooks on this as well. So Qiskit is sort of broken up into 4 sections or elements. You have Terra, which is for building actual circuits. You have Aqua, which is for algorithm development. You have Air, which is for the actual using the quantum computers as a backend / simulating that. And then you have Ignis, which is entirely for error mitigation because quantum computers make a lot of mistakes at the minute. So hopefully this video plays, but this video here is basically a quick idea of how to get started. You build your circuit. You can draw it here, which is a very basic circuit on 2 qubits. It is a Hadamard gate and a controlled X gate, and then at the very end we measure each of those qubits. You can define your backend. In this case it's a simulator that I just ran on my laptop, online, as if it was my laptop. And then this circuit has a 50% chance of 0, 0 or 1, 1 being the end result. That is an ideal case of what should happen. We're pretty confident that it works, so we can then start running it on a real quantum computer. You can see here that we're using the IBM Q16 Melbourne quantum computer. I think it has 15 qubits on it, and it just takes a while to run because it is in a queue with other people in the world. And you can monitor your jobs as they're being executed, and then whenever this runs, we'll be able to see the difference between a simulator and a real quantum computer. So it takes some time sometimes. As we can see here, my job is queued number 1. And it should be any second now. It is running. We're going to get the result any second. So what we're going to see is that a quantum computer makes a lot of mistakes. So ideally we have 0, 0 and 1, 1, which is what the simulator told us. But because of noise and because of a quantum computer just making a lot of mistakes, we have some 0, 1 and 1, 0 in the middle, which is a mistake. We did no error mitigation in this circuit. We didn't use Qiskit Ignis at all. But this is basically a quick summary of how easy it is to set up a circuit, but also the mistakes that a real quantum computer can make in the modern day. Okay, so upon watching all of this back, I realized that there actually is quite a gap in the video recording between each slide, but I promised for all the other slides this was all one continuous recording, but I noticed I made a mistake on this slide, so I'm going to go back and fix that. So, Qiskit Terra allows us to build a circuit, so we can see here that we define that we want 2 qubits, 2 classical bits, and that's how we build our circuit. The classical bits basically allow us to take our measurements of what the results are, or the classical register of bits, sorry. This is where we build our circuit, so it's a Hadamard gate acting on the first qubit and a control X gate acting between the first qubit and the second qubit. I'm not going to go too much into the maths as that will just overwhelm you. And then we can measure the results at the end of the circuit being run. In this case we run it on a simulator because it is faster, easier, and it is a good way to test locally that your circuit is working as you expected. And you can run that on your simulator and you can get the results like that. So with Qiskit Air, that allows you to run it on, sort of play a bit more with the simulators and the real quantum computers. So what I foolishly said last time, the first time that I was recording this, I said that in this case we were using a real quantum computer with error mitigation. But what actually happened is that this is a simulator with noise being simulated as if it is a real quantum computer. Whereas the mistake I made last time was I said that this line here was error mitigation, which it's not. Similar to the last time, it is the same circuit, except we are running a noisy simulation. So that's actually really good to run, in that whenever you're confident that your ideal quantum computer's results make sense, you can run it on a noisy simulator just to see what kind of mistakes you can expect to make, and then after that you can run it on a real computer. Qiskit off to the side, I'm not going to focus too much on, but basically it's important to note that we have some pre-made algorithms ready to be used, and it's pretty easy to use. You define your backend here. Can't go over my face too much because I'm in the bottom corner, and you can define your algorithm there, and you can run it. I'm scribbling over a lot of stuff, but it's pretty cool to see how all of these pieces fit together. So one thing I haven't covered is Qiskit Ignis, which is error mitigation. I'll be honest, it's what I've got the least experience in. I'm more of an algorithm development kind of person. But yeah, there you go. Okay, so here are some resources for getting stuck into Qiskit. For me, the main one is the textbook here. It is what I used for getting started off. I recommend some reasonable confidence in linear algebra, but you don't need a physics degree or anything like that. The textbook takes through everything you need to know about Qiskit. If you want something a bit more fun, perhaps, one of the members of the IBM team created Qiskit blocks, sort of like quantum Minecraft, and it has lots of different, down here, has lots of different puzzles. It's actually very kid friendly too, and it's amazing invention, so it is. Anyone else who wants to get stuck into Qiskit but maybe isn't too hung up on learning as much of the theory behind quantum mechanics, there is a open source repository for Qiskit where you could maybe work on perhaps configuring how to construct jobs for the backends, connecting different quantum computers together, testing, documentation, sorry. There's also a huge community within Qiskit translating the docs between different languages for accessibility. And there's also this YouTube channel here, which I find really great too. I spend a lot of my time on the Qiskit Slack. It has a huge community there of people helping each other out. So yeah, there's some good resources, but the number one thing I recommend is the textbook. If you are interested in perhaps working on it together, I would be keen to perhaps do some textbook reading group kind of thing with Northern Ireland. But yeah, that's everything you need really to make a good stab at getting involved in Qiskit. So overall, thank you for listening to me. I hope that talk wasn't too overwhelming. It is a very dense topic that is still very much in its youth, but it's really exciting to see a big community starting to take form. There's my email address, there's my Twitter if you want to chat to me, and thank you to the Northern Ireland Dev Conference team for letting me speak. I think this is a field with a lot of potential, really exciting, people are lovely, and if you're looking something side project that'll be a bit different, fire away. I think has a lot of potential, and I'm really excited to hear what you all think of the talk. So thank you.